All right, welcome to today's webinar. Today's topic is water in mining numerical model applications. This is an Ask the Experts webinar, which means that we have a panel of experts here today who are ready and willing to answer your question related to today's topic. And this webinar will run for 90 minutes, and we'll get started now. So this webinar is brought to you by the Geotechnical Center of Excellence at the University of Arizona. We are industry funded and member led, and we are an interdisciplinary center who works across academia, industry, and fields of study with the goal of bridging gaps within and creating a collaborative platform for geotechnical research and education. If you're interested in learning more about the GCE, we'd be happy to speak with you. Send us an email, check us out on LinkedIn. And we also have a website with lots of information there. And the topic in this course today is related to a section of a course that's currently running through the GCE, which is Water in Mine Operations and Slope Stability. This is section 3, which relates to numerical model applications. But the rest of the course includes information such as you see here on the screen. So if you're interested in this course, you can use that QR code there, or I believe Allison will be posting in the chat a link to learn more about the water course. And many of the people on our panel today are also presenters in the water course. And that course is developed in partnership with both Pateau Associates and also the Large Open Pit Project, who provided development support for the initial run of the course. And of course, we must thank our GCE membership. Without our members who provide funding and support for both our courses and our research projects and webinars such as this, we wouldn't be able to do what we do. So thank you so much to all of our supporting members. If you're interested in membership, again, contact the GCE. We'd be happy to talk more with you. And now to introduce who's here today. So first of all, the GCE webinar team, myself, I'm Jillian Noonan. I am a senior R&D engineer with the GCE, and I'll be your moderator today. And then along with me from the GCE, I have Allison Brucey, who is our program coordinator. Good morning, Allison.
Morning, Jillian. Hi, everybody. Thank you for being here.
And also Christian Ortman, who is a computing sciences researcher. Christian, thanks for your help today.
I think Christian's Wi-Fi.
I think we might have lost Christian temporarily. Hopefully he'll be rejoining us. We also have Julia Potter here, who is the director of the GCE. Julia, nice to have you.
Thanks, Jill. Good morning, everyone. Thanks for being here today.
And then I'm very pleased to introduce our expert panel today, who will be addressing all of your questions. We have Jeff Beal, who is Global Technical Advisor with Pateau Associates. Jeff, always great to have you in our webinars.
Thank you, Jill, and hi, everybody. Look forward to some good discussions.
And Jeremy Dowling. Jeremy is Hydrogeology Advisor and President of Pateau Associates. Jeremy, nice to have you.
Morning, everybody. Nice to be here.
And Phil DeGraff. Phil is Director and Principal Engineer with Giraffe Mining Consultants, as well as one of the presenters in our course. Phil, great to have you.
Thanks, Jill. Hi, all. Good to be here.
And I should also mention that Jeff and Jeremy, who I just announced, are the lead technical advisors for the Water and Mine Operations and Slope Stability course as well. So we appreciate their contributions there. Also joining our panel today is Jim Weigel. Jim is Principal Hydrogeologist with Rio Tinto Kennecott Copper at the Bingham Canyon Mine. Jim, great to have you.
Yes, good morning, good afternoon, and good evening.
And Travis White, who is Principal Hydrogeologist with Anglo American, joining us from South Africa today. Travis, wonderful to see you.
Hi, everyone, and thanks, Jill. Great to be here.
And we have John Rupp. John is a Principal Hydrogeologist out of Reno with Pateau Associates. John, we're very pleased to have you on our panel today. Thank you.
Thank you, Jill. Welcome to everybody across the world.
All right, so that's our panel today. And as I mentioned, they are here to address questions from both our live attendees today. We also have pre-submitted questions that came through from course participants in the water course, as well as through the survey that was associated with the registration link for this webinar. So we have a number of questions to go through, and we'll be accepting live questions also all throughout the webinar. And just for some information for those participants in the webinar today, first of all, you are muted, your video is off. The way that you'll communicate with us today is either through the chat, as you already have been doing, to tell us where you're from and say hello. But primarily, all of your questions should go into the Q&A, which is another button on your control panel. So if you click on Q&A, it should pop up a window, and in that window, you're able to type questions. There is a checkbox where you can click to submit them anonymously if you wish. So please use the Q&A throughout this webinar to address or to submit any questions related to numerical model applications with regards to water and mining. You do have the option to also vote for questions with a thumbs up in that Q&A window. So if you see a question someone else has submitted that you particularly like, you can give it a vote, and we will pull questions that have higher ratings, first. And this is a recorded webinar, which will be posted to the Watercourse site and also to the GC's YouTube page for later viewing. And then we also want to note that the views and opinions that are expressed today are our panelists' own and do not necessarily reflect those of the GCE or any affiliated organizations. And the content in this webinar is intended for educational purposes only. And if you have issues at your site, we definitely do recommend for you to seek out specific professional advice and analysis. And thank you for joining us. So today's topic is numerical model applications. This webinar is one of a series of webinars associated with the Water and Mine Operations and Slope Stability course. So today's topics, some suggestions of what you might want to ask questions related to would be planning of numerical models, water input to geotechnical analysis, or 2D, 3D, and coupled groundwater and pore pressure models. So things around those topics. All right, so now we have the introductory section of the webinar done, and we'll move into the question and answer section of the webinar. So we'll start off with some pre-submitted questions, but at this point, I will invite anyone who's in live attendance to begin entering questions into the Q&A in your control panel. So we'll start off with this first question here, and this came in from the survey, and it's just sort of may set the stage for why are we talking about what we're talking about today? Why is modeling important, and what are we looking at and for? So I'll first direct this question towards Jeff Beal. I'll read out each question, and then we'll open it up to the panel to respond. So this question came in from David. And David asks, in what manner does water pressure influence the geotechnical parameters of rocks, and how does it influence slope stability analysis? So Jeff, if you want to just talk a little bit about this to get us started.
Okay, so the main influence is on the term effective stress. So if you can think about a plane or two surfaces, or you rub your hands together, or two plates of glass together, they're held together, and any geotechnical surface is held together by the weight of material above that surface. So the weight of the material holds that surface together. The more weight, the more the frictional resistance on that surface, and the greater the shear strength on that surface. So if you put water onto that surface, it provides an upward pressure which counteracts the weight of the material above the surface. So I often illustrate it by thinking of two plates of glass, and they can be flat or inclined. In a slope, the surfaces would typically be inclined. So if you have the two plates of glass with no water, then you've got good frictional resistance. It's difficult to move them. As soon as you put a bit of water in, you increase, you create an upward force on the top plate of glass, or the upward force on the top surface. And it reduces the effect of the downward weight. So it reduces the effect of the downward stress. So it reduces the effective stress. And the more you press on that glass, the greater the water pressure becomes, and the more easy it is for those plates of glass to move. So those plates of glass may be any surface. So what the water does is provide an upward force which counteracts or which reduces the effect of the downward weight, the downward stress, and reduces the frictional resistance on that surface, and reduces consequently the shear strength on that surface. So that's the prime influence of water. Now, it doesn't necessarily need to be a fracture surface. It doesn't necessarily need to be a surface. It applies also to a porous medium. So if you can just imagine the sand grains, which are all compressed because of the weight of material above them, and the frictional resistance within that sand occurs because the grains of sand lock together and create a frictional resistance or a shear strength. So now you put water between those grains of sand, it tends to push those grains of sand apart. It has less frictional resistance and therefore less shear strength. So I always say it's a simple concept that's made complicated by geotechnical engineers, but it is really a simple concept. And, you know, it applies to any situation. So it's any shear surface, any medium, if it's got water in it, it reduces the shear strength. It is detrimental to stability. So that's the main thing. There is another component of this which is often ignored and is much more difficult to quantify, but I think in the geotechnical community, we're seeing this as becoming more and more important. And that is the driving force of the water. So if you can think of a slope with, let's say, a tension crack 10 meters behind the slope, and that tension crack dilates because the slope relaxes a little bit because you've mined the material above it. And now you put water in that tension crack, and let's say that tension crack is, let's say, 40 meters high, and you fill it with water, and now you've got 40 meters of water pressure pressing against the 10 meters of confining material between that tension crack or fracture or dilated fracture or joint set. So you got 40 meters of water pressure pressing against the material that's holding that tension crack together in the slope. So the force of that water wants to push the slope outwards. And so the driving force of the water is also really the second way that water influences geotechnical stability. It's harder to quantify, but I think we're seeing the influence of that more and more, particularly where we have structures which are parallel to the slope and therefore dilate. Water gets in them, and the force of water causes the slope to become unstable. So those are the two things: the effective stress concept and the driving pressure of water. Sorry that took a while, but there you go.
I think that was a great explanation. And I would also encourage those who have a similar type question, or want to know more about that all of this sort of fundamental content like this is included in the water course in earlier sections. But we thought it'd be a great way to lay out just what we're talking about today, and the significance of water, and why it's important to be assessing it and understanding it when you're working with mining slopes or underground mining. Any other comments to add from the panel before we move on to additional questions?
Sure, Gillian, I'll add to that a little bit. I suppose the other element is the time factor, in that very seldomly are groundwater conditions static. So the one end member is the transient pore pressure changes due to rainfall or freshets, snow melts, and that type of thing, with a high peak of pore pressure that dissipates quite readily. And the other end member on that aspect would be long-term fluctuations, and there've been a couple of PhDs that have investigated this in more detail, demonstrating that there is actually a fair bit of ongoing rock mass damage with cyclical pore pressure loading and unloading, contributing to degrading of rock mass and joint strength as well. So that the temporal aspect needs to be considered as well in this process.
Yeah, totally agree.
All right, thank you very much for that question, Daniel, and for starting us off today. We're going to go through some more pre-submitted questions, but I'll remind our live attendees today that the Q&A is now open and you are welcome to enter your questions at any time. So going into our next question that came in from one of the participants of the water course, and this is on the RU factor. The question is, which range of RU factor can we use for stability analysis in the following situation? Water coming from infiltration of rain, underground flow through a permeable alluvium, perched water. And then a second part to that question is there a reference with equivalences of water conditions and RU factor recommendations? So I'll open that up to the panel. I know, Phil, you do talk a bit about this in your presentation in the course. Would you like to start?
Sure. I think the short answer would be to refer any interested readers to Lauren Loring's paper at the Slope Stability Conference in Belo Horizonte earlier this year. He goes through a process of how to estimate RU factors, and the approach that he follows has been calibrated with actual data from other case studies. So I think often these RU numbers seem to be quite heavily overestimated, and then are I suppose can be very pessimistic unless they are ground truth with some real practical data. So I mean, RU factors that are greater than 0.2 for hard rock conditions are extremely pessimistic. I'm sure Jeff's got more to add to that.
And I'll just note really quickly too, Jeff, that I'll try to pull that reference you just mentioned and post it with this recording on the watercourse site.
Yeah, the paper that you put on there, from my paper I think you put on there a couple of weeks ago, has also got quite a bit of reference to RU.
Yeah.
But RU again it's essentially the ratio. It's not quite, but it's essentially the ratio of the downward force to the upward force. It's not quite that, but that's a simple way of saying it. And so because the weight of the rock is typically twice the weight of water, again very simplified, then the RU for hydrostatic conditions. So if you have a situation where the water table is at the surface, the RU is about 0.35, so about a third. So that's a typical RU for hydrostatic conditions. And so for subhydrostatic conditions, i.e. for most slopes, the RU is somewhere below that. And as Phil said, there is often a tendency to overestimate it. When you've got artesian conditions, the RU is above 0.35. So if you say an RU of 0.5, it means you've got an upward force, an upward hydraulic gradient, or a hydrostatic condition, or a water condition which is above the level of the topography or a level of the slope. And so it's used a lot. I mean, it's as Phil I think also mentioned, the best way to figure out what RU is to put piezometers in. And, I think we've been encouraging operators more and more, particularly where you have rainfall and transient conditions, is to, let's say, drill holes which are 30, 40 meters deep and put in a string of, let's say, five piezometers. So you put the piezometers at, let's say, 40, 30, 20, 10, 5 meters down and see what the shallow conditions are. I think the other thing in Lauren's paper is that he points out is that probably more than half of all slope instability globally is related to surface water, shallow infiltration, shallow water. So this is an important factor. And so trying to understand the conditions shallow in the slope is also very, very important. And it's something that the geotechnical community is realizing more and more. No longer are people focusing on overall slope failures, but the focus is tending to shift to shallow conditions, which you see in many more cases.
Yeah, if I could, I would like to jump in here too. We've actually looked at the RU and just from the standpoint of looking at just precipitation events, and then also here at Kennecott, we get a fair bit of our water as snow. And so we've found as we see the largest increases in water during that snow melt period, early spring. In general, across all the site, I think our average RU change in RU due to our snow melt is around 0.08. But then we do have some localized areas that are 0.12 and sometimes a little bit higher than that, just following the snow melt or during a precipitation event. So I don't know if there's like a really good general number to use. My recommendation would be to fall back on your instrumentation and try and develop it for your site, because all sites are different. The RU is going to be affected by the permeability, so how fast the water is coming in and how fast it's able to kind of come out the other end too, so you're not building up those pressures. So, really the literature is a good starting point, but I would encourage all operators to get some actual real data and baseline your operation with the stuff that's bookmarked in those papers.
Yeah, and I think just to reiterate, if you've got shallow instability, keep the instruments fairly shallow.
Yeah, I've seen it used to best effect using a sensitivity-based approach. So especially in very shallow transient parts of the pit slope in the excavation damage zone, for example, the amount of water that's present can be extremely variable because of the distribution of fractures and where the local recharge sources are, and the seasonal nature of recharge and so on. So on a few projects we've worked on with the geotechnical teams, we've used a sensitivity-based approach where we've had a three-dimensional flat model or deformation model, implemented the regional groundwater system with deep piezometric data and a calibrated groundwater flow model, and then the excavation damage zone or the shallow transient groundwater that's more uncertain, we've put a range of RU values into the geotechnical model from 0 to something fairly conservative, and then used it as a kind of a screening tool to try and see which sectors of the slope appear most vulnerable stability-wise to shallow and transient water, and then use that as a basis to try and focus future monitoring. So put piezometers and monitoring instrument in the areas that show the most geotechnical vulnerability to shallow water.
Okay, great answers. Anything else from the panel? And a very good question too as well. Thank you so much. And I will grab that reference mentioned. Jeff mentioned there was a reference that we've already posted associated with one of the previous webinars, one or two, I can't recall, that's in there. And then I'll post the one from Lauren Lorig for Slope Stability 2024 in there as well. So you can read a bit further on that. All right, so we'll move on to our next question. And this came in through the Qualtrics survey that we posted on LinkedIn from Alvaro. So two parts to this question. Firstly, which numerical code is optimal for modeling fractured crystalline media like porphyry copper deposits, allowing for accurate estimation of heads and fluxes? And then the second part, are discrete fracture network or DFN models particularly advantageous for simulating an entire open pit mine? So this I will open up to the panel, and I will just request for anyone that wants to start to go ahead and unmute.
All right, I'll give it a fairly negative go first.
Okay.
I think the answer to the first question is, I always say, is it doesn't matter. The error on which types of numerical models is this. The error on the assumptions is 100 times. So what makes a good model is the geological base, the number of water level measurements you have, the calibration to transient conditions, and the assumptions that you make. So I think it's more and more documented that the biggest source of error in numerical models is poor conceptual models. So I think the answer to that question is it probably doesn't matter, because whatever numerical, some numerical codes do certain things different than others, but in reality, it doesn't really matter. What matters is your assumptions. And so for a DFN model typically assumes that types of fractures, fracture orientations, fracture depths are homogeneous or consistent. And so as we see in the course, for any fracture orientation, for any fracture, the properties of that fracture are very variable on a scale of a foot, 10 feet, 100 feet. And what matters from flow on the fracture isn't the average aperture on the fracture, it's what we call the pinch point on that fracture. And I always illustrate that if you have a flow of water down a 6-inch pipe with a 2-inch valve, it doesn't matter what the size of the pipe is. The only thing that controls the flow is the 2-inch valve. It's the same with fractures. So if you have a pinch point, if the fracture is tight in a certain area, that will control the flow. So you can use DFM models to give you an overall sense of the anisotropy, but it's not good practice to use them too literally, because the nature of every fracture is different. And you'll see if you look at the course, there's an explanation of the representative elemental volume, and that's a good basis to decide what type of modeling and what type of approach you should use. And in virtually all cases or all situations, a fracture flow model is just too theoretical. It really doesn't really capture the reality of the situation. So answer to the question is, it probably doesn't matter. It's the assumptions. Second part of the question is, use a DFN for overall understanding, but not for specific details.
Couldn't agree more, Jeff. I was going to say almost exactly the same thing, is that the code is almost irrelevant compared to having a very good conceptual model supported by a good data set, and then being able to appropriately represent that conceptual model within a numerical framework, and being able to make good decisions about how to simplify within a numerical framework, and being able to support and defend that the assumptions are made in making those simplifications, and that all of those aspects of having a successful model are independent of the code itself. So having a very good conceptual model and a good data set and a good plan to implement the conceptual model into the numerical framework are critical, and much 100 or 1,000 times more important than the code selection.
And that's
Yeah.
actually becoming more and more documented in theoretical texts as well. So
Yeah, I was just going to add that use a code you're comfortable with, that you know that you're not going to spend a bunch of time on a learning curve and dealing with unforced errors and mistakes, so you can focus on the conceptual model. And the other thing I was going to say is I can't think of a single example of where we use DFN in a practical application to a pit scale hydro problem in the 25 years I've been doing this.
Yeah.
Travis,
Yeah,
did you have something to add?
DFN again, the same thing. A lot of fracture systems have no hydraulic conductivity whatsoever. They're clay filled, or they're mineralized, or there are large stresses that render them closed, and so the DFN in and of itself doesn't help with the hydrogeology. It's understanding which of the fractures are important to groundwater flow, and that requires a lot of data and site understanding. So DFNs generally aren't used for monitoring or modeling groundwater flow and pore pressures in open pits.
Yeah, just to maybe add, there's a saying in modeling, right? All models are wrong. Some are just more useful than others, and the use of your model is a function of the inputs, right? So having a robust conceptual model, making sure you've got an extensive monitoring network that you to get the data to convert that into information, and then with respect to the code, there are I won't say it out loud, but we do in Anglo American have a preference. Some codes, are more practical than others, especially within mining, block caving, things like that. But it's going to be a function of the modeling objective. So define your model objective. Make sure you put the work into and the correct technical rigor in defining your conceptual model. And then yes, the code is nearly irrelevant. But some codes are slightly more practical than others for certain applications.
yeah, exactly, Travis. I mean, for the details, and some codes do certain things better than others, but the overall it makes no difference. The control on the answer is the assumptions.
Yeah, if you've got a density dependent or a temperature dependent problem, you got to use a code that captures that kind of thing. Sorry, go ahead, Jim.
Yeah.
I was just going to kind of come full circle on this and say, I agree. You need to have a really good conceptual model. You have to have the framework. You have to have the geology in there. You have to have the instrumentation. But what I find the models to be most useful for is kind of running them and then looking at where am I not matching up with my data? What could be going on, and having those like mental experiments, like, what are the options to get that to actually portray what we're seeing in the field in the code, and is there something I can do about it to do some investigation around there? It's really kind of like telling you how good your conceptual site model is, or identifying areas that you're kind of missing. You're missing the boat, and so what do you need to do? Do you need to go in and do investigative drilling to try and figure out why those heads are lining up that way? You might find that there's a unmapped fault because I don't know about you guys out in the fields and at other sites, but we seem to always find new faults whenever there's a new instability. But the conceptual model is constantly changing. There's a few places in our pit where I'm like, I bet there's a fault in this location. Right now, it's far enough back that we don't necessarily need to investigate, but it's definitely something to think about. It kind of like takes your conceptual model, puts physics to it, and allows you to ask the questions like, why is this not working like we think it should?
Yeah, I mean, I think that's a great point, Jim, the geology and I think much of the instability we see in slopes is because the geology isn't quite what we thought it was. As Jim says, there's a fault that we didn't know, or the orientation of the fault is slightly different. And the same applies to both geotech and hydrogeology models. We can take values of porosity and storage, and we can take values of friction angle and cohesion and so on, and we can run statistics and we can do sensitivity analysis on models. But the overriding control is the geology, and geology does not lend itself to statistical analysis.
Yeah, I just want to piggyback on the point Jim raised. It's an excellent point. And ground truthing, what you see in the model, some of the predictions, identifying gaps, is incredibly important. But another point I want to raise is, we've come across it quite a bit in our company. There's almost an overemphasis on the numerical models. A numerical model is just one tool in your toolbox as a hydrogeologist or a geotechnical engineer. It shouldn't be, the gospel, so to speak. So it's a tool that you use to identify gaps that you can then ground truth and then, make some informed decisions on, but it shouldn't be the only thing that you rely on. You still need to apply analytical methods. You still need to do the field work, characterization, and there should be, that feedback loop into redefining and developing your conceptual model and improving that accuracy. So don't just rely on the numerical model. There's Jeff can give you a few good examples where mines have been landed in trouble by relying too much on what the model said.
More than a few. I think part of the problem that we all face is that numerical models have gotten to be accepted by regulators. And so the regulator who doesn't necessarily understand the situation trusts the model. So that's one problem. And the other problem is that often corporate management and corporate leadership also don't understand the situation, but they trust the model. So that's a situation that we're in, is that models are required by people that don't understand the limitations of models. So as Travis says, in reality, you don't need a model for many applications, but a lot of the times they're forced on us.
I can think of one example in my career where the numerical model has helped better inform the conceptual model. And on almost every project, shortcomings in the numerical model are found and fixed with good site conceptualization.
Yeah.
Great.
Also, a model doesn't need to be a numerical model as well. I mean, you
Correct.
can do a lot with a spreadsheet and some sensitivities. So it doesn't always have to be a numerical solution.
That's a very good point, Phil.
All right, so we've been talking about code and just touched a bit on additional software that might be used, such as just a spreadsheet. So I'll pull up this question from our live group today, asking, are there any open source code packages or software available for modeling pore pressure or coupled groundwater, similar to how ModFlow is used for groundwater modeling? Anything the panel would like to comment on here?
So in the 2D, so all pore pressure is just the head of groundwater in the pore space or the fractures. So it's any numerical code will give you an answer on the pore pressure. so we can use, mod flow, feed flow, any of the standard code will tell you what the pore pressure is. I'm not quite sure what the coupled groundwater is, but if you mean coupled groundwater and geotechnical properties, i.e., the groundwater pressures are dependent on the geotechnical changes to the geotechnical conditions, then a couple of the best codes are in 2D. SEEP-W is very often used for groundwater modeling, particularly in a 2D world. The sister program SIGMA-W, so SEEP-W, SIGMA-W. SIGMA-W will capture the coupling. It'll capture the geotechnical parameters, which are important for understanding groundwater. And that's particularly also important in tailings, where if you're trying to model pore pressure in tailings and tailings consolidates, you pretty much need a coupled solution. So SIGMA-W is good for that. It's a 2D code. And for 3D, I'm not sure I'm not sure. I know the developers of ModFlow and FeedFlow have both been looking at coupled codes. I'm not sure where they're at with that, but one that is able to do it is the geotechnical code FLAC. But the groundwater solutions in FLAC, again, it depends on the assumptions, but FLAC isn't always the best code to use for groundwater, but it does give you a simulation of coupled geotechnical and groundwater conditions. So I don't know whether that answers the question. I think it does.
Just a nuance here, Jeff. I think the question was open source, which I think is like freely available to anyone. So I don't think that there is a freely available open source code
for
coupled groundwater flow. I could be wrong about that. There have been some attempts to use the interbed storage package in ModFlow, and I haven't looked at the latest ModFlow 6 capabilities, but there may be some things in development. It might be worthwhile to anybody who's interested in this to contacting the USGS. In particular, there's a person named Rich Neiswanger in Menlo Park, California at the USGS. He's available for anybody to call, and or email, and they could give you an update on the latest from the USGS, which is, of course, all their stuff is open source. I would say for practical applications, the codes that Jeff mentioned are what we're using at these days, but those are going to cost a few $1,000.
Yeah, I can't think of any open source codes for coupled hydrogeomechanical simulation. It's the Sigma package and FLAC that usually gets used.
Yeah.
All right. Thanks for that input and tips, and thank you for the question. We'll move on to another. So this question also was pre-submitted, coming from Renzo. Have any of the panel had experience comparing the modeling results of fan-shaped versus parallel drain holes for dewatering or depressurizing open pit mines? And additionally, could you discuss the advantages and disadvantages of each configuration and provide real-world examples where applicable? And I will open that up to the panel. Anyone would like to start?
Okay, I'll give it a crack, and I'm going to answer the second bit first. And so we talk about drilling horizontal drains in lines perpendicular to the slope, or in fans. The advantage of a fan is you can keep the drill in the same position and drill multiple holes. And so in terms of the technical merits, if you're drilling a slope with a bunch of subparallel structures, which is often the target for horizontal drains, then it's often better to drill a series of parallel holes to try and go perpendicular through the structure. So if you're in a situation with parallel structure that's parallel behind the slope, drill lines of drain holes. If you have variable structures, structural orientations, or your access to the drill or to the face is limited, so that maybe there's only certain places that you can put the drill without acceptable rockfall risk. And so if you do that, then you might want to do fans of holes all from the one locations. And in terms of model results, I think the main thing with horizontal drains and looking at the benefit is horizontal drains is to install piezometers. And more, we're putting in horizontal piezometers. So before you actually start the drain holes, you put in the first hole or maybe the first dry hole, you make it into a multi-level piezometer, so then you can actually see what the rest of the drains will do, what the rest of the drains are achieving in terms of pressure reduction. So the best way to doing that is with piezometers. Yes, we've had experience comparing the model results for fan shape versus parallel drain holes. But again, it's based on the assumptions, so it's much better to do it with real data if you can.
Travis, you have your hand up, or do you have something to add?
Yeah, Jeff covered a few of the things I was going to say already, but I won't speak to sort of the modeling results, but just from a practical perspective, fans versus parallel drains. The orientation or the geometry of the structure that you're targeting is to a large extent going to dictate which one is better. So like Jeff said, going perpendicular horizontal drains probably better, but it might be easier if you don't know the orientation of the structure, to go in with a fan and then hit the structure that way. The real estate that you have available to drill these holes, it's maybe not always practical to have, a drain every 5, 10, 20 meters. It might be easier to just drill from one platform and have the rig drill through a common collar. One of the benefits of that is managing the water that comes out of the drains is a little easier because you now have one collar to manage. You don't have all the collector pipes. From an underground perspective, generally speaking, the fans are more practical because you can develop dedicated drilling, underground cubbies, and you can park the rig in there and drill your fan. It's not always practical to have, a set of horizontal drains down, on your sidewall down a drive. But again, the orientation is going to be dictated by which option you go with is going to be dictated by the orientation of the structure you're trying to target.
Yeah, I think even if you drill a fan into the pit slope because you're constrained by real estate, it's a good idea to look at the orientation of the fabric, the smaller scale fabric in the rock, and also the larger structures too, and try and orient the fan so that all the drains are perpendicular to that fabric. So you don't just drill a kind of a random kind of cartwheel, half cartwheel kind of shape, but you orient all of the drains in a splay through the fabric and the structures so that you hit more permeable features and get more drainage. And if there are bad acting structures behind the slope, then you get to depressurize those as well. So in any event, whether the drains are just walled parallel in irregular spacing, or if they're fans that are spaced further apart because of operational constraints, then designing that drain program, looking at the geological framework, is always a really important thing to do.
Jim, I see you have your hand up. Did you have something to add?
Yeah, just the comments Jeremy just made around, looking at the structures. One component of that too is just there can be a lot of cost savings on that. We ended up doing that in our underground drainage gallery and reduced the number of drains quite substantially, but oriented the drains, more favorably, and as a result ended up with better depressurization for less money. I missed a bunch of Jeff's stuff, but for some reason my internet failed out. But one, and I think Travis also hit on this, but I mean, we have 2 rigs that are currently running in Bingham Pit as we come down the wall, and we do fans, and it's just we can get more drains in by fanning out, having one drill pad, because for us we have to have drill pads that are isolated from all our haul traffic. So you can imagine like trying to build one of those up every 100 feet down the wall, on the active cut versus putting in one, and then now you're able to just do one every 300 or so feet because your fans are going out into the formations. The other thing too, just a lot of times we're probing for unknown structures too that are back behind the wall that could be holding up water. And we've had a couple instances where we hit something that just pukes out 60, 70 gallons per minute for 24 hours in an active moving zone, and then shortly thereafter the moving zone starts to slow down, and it wasn't necessarily a feature that we had mapped either. So we're constantly just probing behind the walls, seeing what's there. The models say it should be dry, but there are these high angle features that a lot of them that aren't mapped that we will occasionally hit and reduce pressures on. So there's that component too. So I don't know if, I guess it kind of, for us, we use it kind of as a insurance policy as anything else. And while we do put, fan drains in our models, a lot of what we do is just more physical based in what we're seeing. We do try and get, additional piezo's in so we can demonstrate the depressurization. Yeah, that's kind of where we're at. It's kind of one of our insurance policies with our very large walls is just to have that horizontal drain drill rig in place.
Thank you. That's an interesting perspective to hear, Jim. Travis, you have your hand up?
Yeah, so just to add, there's 2 of our operations, we actually had to go with a third configuration, which were vertical and sub-vertical well or bores drilled from the pit crest and sometimes in the pit, just purely because there wasn't access to the face to drill the horizontal drain. So you can also do or implement vertical and sub-vertical wells with, you obviously then have to pump the water out of those. But in these 2 examples, that actually worked out more cost effective because the drilling was significantly cheaper, and we were able to deploy some relatively low cost pumping solutions as well.
And I think this would be a good time too for me to just plug our next webinar, which is going to focus on the implementation of slope depressurization program. That's going to happen on September 18th. So we'll be talking a lot more about these types of topics during that webinar as well. Any additional comments from the panel for this question here before we move on?
Just one other
go ahead, Jim.
Follow up, and it's just, thanks Travis for bringing that up. Horizontals will hit stuff that's more high angle versus like a vertical hole or an angled vertical hole will end up hitting some of those that are more parallel to the benches that could be completely missed by the horizontals. That's all I have to say.
And Jeremy?
Yeah, no, I was just going to say that just on the question about modeling, comparing modeling results. I mean, you can, if you calibrate a 3D model of a slope sector, you can put different densities and configurations of drains into the model and have, scenario 1 and scenario 2, where you've got different arrangements of drains, and you can run those 2 predictive scenarios, and you can have monitoring points in the model at the location of where you might install piezos in the future. and you can compare the results. So you can look at the depressurization response that the model indicates for different configurations of drains. So it's easy to use the model to compare different configurations of drains. But, with similar to the tone of other discussions about the model is that it's just a model, and the practical field data and the piezometric responses you get in the field are what you really need to use to guide and plan the drain drilling program. So the model can kind of help just in a general sense to get an initial kind of feel for what you might be able to achieve with drains. But the practical field data is what you really use to plan the expanded drain programs normally.
All right, thanks, Jeremy. And just an announcement for all of those joining us live today, we have about 30 minutes left in this webinar. So if you do have questions, now would be a good time to answer them. I will also point out to those who have already submitted questions that some of them are being answered by our panelists in writing. So if you click Q&A and you go into the answered tab, you may see that there has been a written answer provided for your question. And I'm going to pull up another question. And John, I know you already started or you typed an answer to this question, but I may ask you to just talk about it a little more for the rest of our people on the recording. I thought this is a good question from Tim asking, is there a sweet spot between complexity, capability, and outcomes in current stability and pore pressure modeling practice? Are there approaches that are more or less reliable for both situations, and anything to avoid or be wary of? So John, since you already started typing an answer to this question, maybe you want to start off?
Yeah, I mean, this one's actually pretty simple. You just want to include just the right amount or the minimum amount of complexity you need to capture the key processes. You don't want to add aspects, detail that doesn't move the needle in terms of the answer and your ability to capture the key processes. So just keep it as simple as you can. And the more complexity you have, the more challenging it is to see what's actually going on, whether you're capturing those processes appropriately. Make sure you focus on, I didn't put this in the answer, I kept it pretty brief, but make sure you don't let the model cloud your understanding of the hydrogeology. You got to be using your understanding to check that the model is right. You need to have a good feeling of what the answer is or what the range of answers should be, rather than relying on the model to tell you what it is. So it's just keeping things simple and only modeling what you need to and not more than that.
Yeah, I mean, I think we start off section 3 in the course with 2 statements. Travis mentioned one earlier on that all models are wrong, some are useful. The other one that I often use is it's better to be approximately right than precisely wrong. So, yeah, just avoid complexity that you cannot justify.
Or back it up. I mean, if you don't have data, then you're just guessing. That verification of the outcomes is critical. Otherwise, you're fooling yourself with complexity that just creates pretty pictures and doesn't help you in your understanding or management of the slope.
Yeah, I'm answering a question on that right now, Phil. We're getting some questions here of, well, what do you do if you don't have enough data? How do you fill it in? Well, the answer is get more data. One of the most important things we can do is to convince our clients that we need more data. This isn't what we have isn't enough. It's a hard thing to do if you're not experienced with it, but sometimes we have to draw a line and say, look, to be able to get the right answer, we need more data.
So there's a project that we're working on at the moment, a large project that's in feasibility, and we haven't been able to get large-scale pumping trials done. So we've got a real problem. And so we've got a model, and the model spits out answers, and those answers cannot be verified because we haven't got any large-scale trials to give us a good transient understanding of conditions. And so we're in a situation where the client wants more and more modeling without the backup. But the way I think we've handled this is benchmarking. So we've gone and looked at all sites which are similar to the one we're working on, got data from those sites, and used the benchmark sites to understand the conditions that we're likely to get at the site we're working on. So if you're in that situation, I always say that whatever you do in mining, somebody somewhere has done it before. So benchmarking is a good way to help validate conditions.
Very good. And thank you, Tim, for the question. Any other comments from the panel?
I think that there should be a lot of emphasis on monitoring instead of complex numerical modeling. So especially with the pit slope pore pressure modeling that is done to inform geotechnical models, I think oftentimes the best approach is to put some relatively simple groundwater assumptions into the geotechnical model, and then complete the design analysis, and then use a good program of monitoring to confirm that the field conditions are compliant with the assumptions of the design, and also to identify areas that aren't compliant with the design, and then use that to target depressurization. So I think that workflow and the use of simple inputs to the simple groundwater inputs to the geotechnical models, and a really good monitoring program is much better than trying to do a lot of really complex quote unquote pore pressure modeling that is then put into the design analysis.
Exactly, Jim. That often can help you figure out whether pore pressure is even going to be an issue or not. I mean, it can screen it right in the first instance, and concentrate on areas where it is important.
Exactly.
100%. Yeah, 100%.
Good. All right, I'm going to pull up another question from our live group today that sort of flows well with the current conversation that we've been having. So what are the current approaches to quantify uncertainty in model predictions? And how is this uncertainty communicated to decision makers? And I might also include in that, Jeff Gill mentioned that regulators often use these models. So how do you quantify and communicate that uncertainty that is present in your models?
I actually answered this one. Can I?
John, I was going to say, I know you typed an answer, so I was going to ask if you wanted to start. Yeah.
If it's okay, guys. So normally the two most common used are either stochastic methods. So you have a statistical distribution on your inputs, and then you get an ensemble on your uncertainty, and then there's bracketing with deterministic uncertainties. And my experience is stochastic tends to wash things out. You're better off understanding what the key drivers are on your uncertainty and using a deterministic end members. Once you've got a good, robust sensitivity analysis, then it's typically communicating the risk trade-offs. Okay, so what's the level of the risk? What's the likelihood and consequence tied to that? And then the trade-offs for mitigation measures. So, for every risk that I have, if I can manage it with some kind of mitigation measure, what's that cost trade-off? And so that's how owners typically like to receive the information. In my experience, I'll open up to everybody else to.
Yeah, I think, John, I mean, as we said earlier on, you can do a stochastic analysis, but you can't do stochastic analysis on geology. And it's the geology that's the ultimate control. So, I mean, I think the best thing you can always do, as Jeremy said, is do trials. Go get data in the field and use that to validate the models.
Yeah, I think something that, I mean, in terms of pit slope pore pressures, the biggest uncertainty or the factor that causes the field conditions to greatly deviate from predictions is it can be the geologic or the hydrogeologic uncertainty and the uncertainty in the hydrogeological parameters, which are often considered in classic groundwater modeling uncertainty analysis is, you know, what's the uncertainty in my K values or my storage values. So that's the kind of classic uncertainty analysis that's thought about with groundwater models. But 8 times out of 10, that uncertainty is irrelevant for pore pressures compared to things like the operational implementation of the dewatering system that was assumed in the predictions, right? So a set of predictions in the groundwater model that could be done to support a pit slope design, they might assume there's 4 dewatering wells and numerous horizontal drains included in the slope implementation to create depressurization that is needed for geotechnical stability. So that's the assumption in the model, in the predictive model for the design. But then when the slope's implemented, the wells don't happen and the drains don't happen. And for that reason, the pore pressures are vastly different to what was predicted and what was assumed in the analysis. And that creates a much more significant deviation in the pore pressure regime in reality compared to the classic kind of uncertainties in the hydrogeological model and its parameters, and that is often overlooked.
Totally, yeah. Good answer.
Jim, did you have something to add?
Yeah, 2 things, if I remember them both. But one of the approaches that we use to kind of get at the uncertainty is to actually run a series of sensitivities where we up the pressure to the phreatic surface by known units. For us, we'll run like a 50 feet of additional head up to, you know, well, 100 feet and then like 300 feet of additional head. And then we'll run those through the models to see how the geotech models behave with those additional head values. We'll also run a series of RUs through them too, just to try and get at some of the more shallow slope failures just due to transients. So there's a number of things that we do just to see what's going on, and then we can take those learnings and see, you know, is this something that, like, if we put in additional horizontal drains or a well, can we make the slope behave better based on the modeling effects? And then the other component I just wanted to mention too is if you are looking at doing a long-term project, it's multiple years long, you know, as Jeremy pointed out, make sure that the proper depressurization is going in, but also don't forget, you probably have new data. It might be time to update your approaches, update your models, revisit your predictions. Anytime you start getting out from that calibration period and going into predictive mode, you'll find that your models are pretty close on at the beginning, but then things are changing. And the further away from your predictive, benchmark going forward into prediction mode, usually the more you start seeing deviation. So it shouldn't be like a one and done cycle, especially if you're on projects that last 5 or 7 years. You should have like a reiteration component every 1 to 2 years at the most, because you're learning stuff as you're mining down. The geology is changing. The assumptions of the geology have been updated. So why shouldn't you update your conceptual models and your numerical models at the same time?
Yeah.
Just to build a bit on the first thing you said, Jim, I mean, I think what the bottom line for slope stability is head or pressure. So I've always liked your approach of varying the head in the numerical model, which is the bottom line of what you're trying to predict, rather than varying permeability or storage. Because by varying head, you're giving a direct input to the geotechnical analysis. So I've always liked that approach you've taken of varying the head. By, as you say, increase by 50 or decrease by 50. I think that's a good way to do it.
Well, I mean, yeah, that's what we're here for, is basically evaluating what the head changes do to the pit slopes. That's the kind of the big difference between modeling for a pit slope versus doing, modeling for water resources, is the way you approach your
It
sensitivities.
complicates the process as well.
Yeah.
It makes it simple. Everybody can understand it, right? And it's
Totally.
very practical.
Totally.
Yeah, I think it's a good approach too.
Great. I think we covered that question really well. Any additional comments before we move to the next? All right, so we have another question that came in from our live group that I will pull up because Jim was just talking about, updating models as mines grow deeper. And this question relates to deep mines that have planned final slope heights in the range of 1,000 to 1,500 meters or more, but there is still not much precedence for such high slopes. So the question is, as mines get deeper, can we keep the same numerical modeling methodologies and hydrogeological characterization? Or do you know if the LOP project is actively analyzing these changes? Again, I know, John, you started off typing an answer, so maybe I'll have you start and then pass off for additional comments.
Yeah, actually, it'd be great if Jim would answer this one. He's doing this every day in a 1,200 meter deep pit. So I put out some initial thoughts, but I'd like to hear what Jim has to say, and others who are working in these big pits.
Jim?
Where do I start? I mean, what we do have advantages of is having long data histories. So I would say a lot of what we're also relying on is just our data history with our piezometers. We're watching the drain down as the slope progresses. We're watching, for things that are not behaving the way we expect them to do. I think, it's a difference between like a brownfield site and a greenfield site in some respects. We still have to have hydraulic inputs, so you still need to have the pumping wells, or for us, we operate a bunch of wells into underground workings that can affect very large extents of the rock mass. And we use kind of natural pump tests, if you will, and they happen anytime one of our big pumps goes down. The motors usually burn out, or we wear out impellers, and it goes off for 2 to 6 weeks, say. And so we have our recharge period. So that's kind of like, our, giant slug test, and we're watching the waters come up. And so that gives us a lot of data sets for evaluating the pore pressures, both in the immediate vicinity of these underground workings, but also across structures. We effectively did this for our underground operation here at Kennecott too, where we have the North Lower Chute shaft, and we basically said, hey, we're going to turn it off for a period of time, and we set all our instruments in the area up to a higher frequency of data collection, and we were able to just turn off the pumps and then see how the water moved across structures, and we're able to use that. So we do a lot of large scale tests from using our underground workings and our big pumping systems. So I still think that, you still are using very similar hydrogeologic characterization methods. I think they're still as important. But I would also say that, for us, and for any pit that starts getting really deep, don't discount the history that you've accumulated from all your piezometer instruments over time. I mean, that's still very valuable data. You just have to put it in the right mine planned and mine development rates. So oftentimes what I find is I'd much rather stick in, 3 different strings of instruments than say one pumping well and do a aquifer test on that one pumping well. Those 3 different sets of instruments or strings of instruments can be way more insightful than one pumping well, where you might not be able to see the effects of that pumping well more than 150 or 200 feet away. So, it's a trade-off, and a lot of it's dictated by the lithology and the structures that are at play at your site. But I still think you still need to have all the various information and look at it. I don't think that's really changing as the pits change.
No, I mean, I think the answer to the question is you keep the same methodology, and it comes down to fundamental understanding the conceptual model and monitoring it. For very large pits or very high slopes, the stresses in the slope can change and become more, and an approach that many of the big pits have either considered or implemented is the idea of a drainage tunnel, because the consequences of an overall slope failure are that much greater if you've got a bigger slope. And so, to take your example, Jim, you took the proactive measure of putting in a drainage tunnel all the way around the toe of your slopes. And what that's enabled you to do is have confidence that you can vary the mine plan without having a major, without major implications on the overall slope performance due to water. So that the lower part of your slopes are well depressurized. So you have that comfort and you have that mine planning flexibility that you can work within that. And I think that is the difference. If you've got very big pits, if you look at the drainage tunnels that have been put in, they're not all in big pits, but many of them have been in big pits. If you look at I guess the 3 biggest pits are Bingham Canyon, Chuquicamata, and Escondida, and they've all had drainage tunnels put into them. So I think that's mainly the difference, is that when you go for these big walls, it may make the idea of a drainage tunnel that more attractive.
Yeah, I just want to also put in one more thing too, is you need to have, because you need some breaks in the slopes where you can put in piezometers mid-slope. So if you don't, you become completely blind, or you put them in only to lose access to them, and then they go down because they're hit by a rock or any number of things. But you have to have periodic wide catch benches where you can maintain permanent access so you can continue your monitoring. Otherwise, you kind of go blind a little bit. So that was a kind of a big learning as we developed from slice 1 to putting in slice 2, as we're leaving behind these 75-foot to 100-foot wide benches where we can put instrumentation, both hydrogeologic and downhole geotechnical instrumentation. It's really been kind of a game changer. It's also going to kind of opened up something we hadn't really thought of, and we're actually next year going to put in a number of wells to depressurize ahead of our next slice coming down. So we're going to drive the wells deeper below the current mine bench and down into where the existing slope's going to kind of end up. So do some pre-depressurization mid-slope with one of these wider catch benches.
Go ahead, Travis.
Yeah, just maybe slightly off track, but one of the other big benefits of having a drainage gallery or drainage tunnel is it allows you, and Jim, correct me if I'm wrong, but you the plan is to use that as one of the access drives for the underground mine. And if your open pit is going down to 1,000 or 1,500 meters, there is going to be a point where you transition to underground mining. So there's a good additional benefit that if you develop a drainage gallery and at the right point in time, that can act as early access or permanent access for the underground mine in future, as well as some cheap, well, not cheaper to build a gallery, but you'd have access for resource characterization. So you can do drilling from underground to better characterize the resource.
I think that significant change in consequence with these very high slopes is a complete change in mindset about managing and then designing as well. So in terms of the numerical modeling methodologies, certainly from a geotechnical stability model perspective, you'd be running several different types of model and making sure that you could capture the right mode of instability with those larger slopes. You probably wouldn't be messing around with any limit equilibrium analyses. You're certainly into numerical modeling, 2D and 3D models with like John mentioned, a lot of instrumentation to back it up, and the consequence will help pay for all of that extra rigor in the process.
All right. We have less than 10 minutes left in the webinar. I will remind those joining us live, if you have submitted a question, there are a number of questions that have been answered in writing in the Q&A window. So you can click in there and go see if your question has been addressed that way. I'm going to pull up one final question for this webinar. We touched just a bit just now on underground mines. And so for the last 6 minutes here, maybe just talking a bit about numerical model applications and how that applies to underground mines. So for underground mines, what are the best practices for representing mining operations? Please consider aspects such as boundary conditions, discrete features, if applicable, transient material properties, etc. So just a general discussion to close out this webinar on, we talked a lot about open pit. What might we need to consider for modeling underground mines? So I open up that to the panel. Anyone would like to start?
Okay, I'm going to jump in on this one first. And a big issue with many underground mines is ungrouted exploration drill holes. And there are many, many underground mines that we're working on at the moment where most of the problem is due to water coming down from near surface in exploration drill holes. So that is a key consideration when it comes to trying to characterize it and to try and interpret the results of testing. There's one mine, 1,500 deep mine that I've worked at for many, many years, and 20 odd years ago, we got to the point where we could, where we were having full hydrostatic conditions 1,500 meters below surface. So we're looking at 150 bar ahead of tunnels, purely because it was connecting to the surface through old exploration drill holes. So we implemented a program 20 years ago of mining towards the exploration drill holes and pressure grouting the formation close to, and trying to frack the formation and drive cement and cement the exploration drill holes, which we were able to do successfully, and they've been doing it ever since 20 years later. So before anybody else jumps in, I'll mention the perils of exploration drill holes, which are typically good for open pits because they help depressurize the slope, but bad for underground because they bring water down to the workings. I mean, most, once you get, 1,000 meters or even 500 meters, the rock gets quite tight. So it is often the exploration holes which give you the problems.
Yeah, we're getting to be a bit of a broken record here on this, but it's about the monitoring too. I mean,
Yeah.
to be able to figure out what Jeff's talking about, you got to have a good monitoring program. And particularly during exploration, operators get a little frustrated with, when their, operational goals are based around executing a certain number of footage, that they're going to stop and install vibrating wire piezometers, the challenging, 1,000-foot uphill hole, but it has to be done. If you don't have the data to understand the hydrogeologic model, you're just not going to be able to address the underground mine hydrogeology.
So the bit about transient material properties in there is obviously very applicable to caving operations, where you turn a rock which is maybe 0.1% porosity into a rubble which is 20+% porosity. So you generate an awful lot of storage which can soak up water from the surface. So, if you're looking at block caves, the transient changes in material properties is something that it's very important to consider.
Go ahead, Travis.
Jill, I'm going to nominate Pateau to add the diamond drill hole analysis that we did in Anglo-American into the coursework next year. We did exactly what Jeff mentioned. We've done it on a few operations now, and it's a great piece of work, good methodology, and helps mitigate that risk that Jeff mentioned.
It does, yeah. You've still got to deal with it though.
Yeah, but at least through that analysis, you know what you're dealing with. There's a lot of operations that don't even do that up front. So yeah, we've fortunately not learned the hard way. We've done the good science up front. It's paying dividends now.
There was a mine there was a mine I worked at early in my career, which was making about 1,500 liters a second, i.e., lots of water. And before I had the experience to think too much about exploration drill holes, we were all trying to deal with it underground. And it wasn't until that mine closed and the groundwater system completely recovered in about 12 months that I realized that all the water was going down exploration drill holes. So it's something that I personally have learned from hard experience.
I guess the other thing needs to be answered here is there are two main approaches that are being used, like an equivalent storage approach. Like if you're purely in the practices of representing the operations themselves, the tunnels and the stopes, you can use an equivalent storage, or you can use a discrete feature, and it sort of depends. If you have a drift going through a large mass, a crystalline bedrock, it's really tight, then probably a discrete feature is going to be the way to go. You would need to use really small model cells to capture it with equivalent storage. But if you've got a block cave or some larger stopes that scale well to the grid size, then you can use an equivalent storage, like a high storage zone. You want to make sure that you're capturing the evolution of voids from the native rock to a void space, and then also any backfill that's going to happen. And you also, you don't necessarily have to include those as transient material properties. You can break that up with your predictive simulations. The bottom line is, though, you just got to make sure that your response, hydraulic response to whatever you've applied makes sense. You have different choices, and when you apply those choices, you have to verify that the model's working.
All right.
That looks like a hint, Jill.
Well, it's my job to not keep everyone past what they promised. But thank you so much for those closing comments, John. And I just want to say big thank you to our panel today. You guys are amazing. We answered a lot of questions, and you did so expertly, as the experts you are. So we really appreciate your time today. Our participants really appreciate your time today. And I want to thank the participants also for joining us, and I hope we'll see you at an upcoming webinar. If you'd like to be alerted of those, follow the GCE on LinkedIn or sign up for our mailing list. I think Allison put a a link in the chat that you can click. And yeah, thank you so much, everyone. I hope you have a great rest of your day or evening.
Thanks, everybody.
All right, thanks
Bye.
everybody for attending. Good to see you all.
Thanks all.
Good seeing everybody.
Thank you, everyone.